Hey, grade nines. So I would just want to go over the lesson that we just covered, which is transformation of common functions. And I know I went through this in class with cohort A, but I know cohort B, you probably had a couple more questions about this. So I figured I'd just make a video just to kind of briefly recap this. So I did actually attach the first part of the lesson that had video recorded using Teams, but obviously I wasn't able to record the whole lesson, so I figured I'd just do it all here. So I'm going to quickly go through the first part because the first part should be pretty simple. The first page there, we're just really graphing the common um, parent functions that we discussed before. So we have the square root function, and obviously, if you recall, the square root function has y values. If the x values are 0, 1, 4, 9, and we did that on purpose, because we want them to be perfect squares, we can see that the y values would be 0, 1, 2, and 3. And then when we plot them out, we're going to have 0, 0, 1, 1, and then we have 4 and 2, which is approximately right here. And I will actually use decimals later on to graph this out, but for now, it's relatively easy to show this graph. So it looks roughly like this. So again, I was able to do this in the class. I think the video recording that I did with Teams that I posted in the activity feed, you should be able to see how I went over this. But I figured I'll recap all this as well. So our next example, we have our absolute value function. And again, with the absolute value function, what you're doing is you're essentially just taking, you're finding the distance from 0. So that means that we don't actually need to consider the sign, whether it's positive or negative, it's always going to be positive. So in our case, we have a y value of 2, then 1, 0, 1, and 2. And we discussed this already, so I'm not going to do it in as much detail. So this is what the parent function looks like, or we sometimes will call this the base function as well. And it just kind of roughly looks like that. And obviously it's a little bit off, but this gives you a little bit of an idea there. So it's still not going to be perfect, but hopefully that gives you a decent idea of what it looks like. And of course, the last one here is always a bit tricky. It's going to be negative a half. And again, the way the numbers are structured, it's not going to look very nice, but it looks roughly speaking like this. So it's going to be negative 2, and then this is going to be 2, and this is going to be 1 and a half. So roughly speaking, it kind of looks like this. So we have negative half goes with 2, negative 2 there. And then this one right here goes to a half and 2. And then, of course, we have 1 and 1. And then, of course, the last one we have 2 and negative, and sorry, 2 and a half. So this last one, reciprocal functions, I mentioned this already, these are always tricky to graph. And this is definitely, I will not put a question where you have to graph with the reciprocal functions. So I can tell you that right now, it's not going to be on there. So you can definitely ignore this one, but you should be able to at least, at the very least, recognize what the transformation looks like. So that's what the reciprocal function looks like. So what we're doing now is we're essentially making small adjustments to the graph and then adding, but we're basically transforming it step by step, kind of like what you did with quadratic functions. And we're just trying to see in general what happens with the transformation. So I know I went through, I even posted on the announcements what the answer should have been there, but I figured the best thing to do is actually show you on Desmos what's happening to each of these graphs. So I'm going to start off with the quadratic function because that's probably the one that you're most familiar with. And again, this is our base graph here. And what we're going to do is try to see what effect the transformations have. So I'm going to start off with the A transformation and see what it does to our graph. So let's say that this is our original base function, or our parent function, which is y is equal to x squared. So first we identify the key points. So it's going to be negative 2. And I just want to make sure that the screen is being shared. Sorry, guys. Let me just double check. Yeah, I think it should be sharing here. Perfect. I myself just want to make sure that this is all being recorded. Perfect. So first thing we notice is that our key points are negative 2 and 4, negative 1 and 1, 0, 0, 1 and 1, and then of course 2 and 4. So these points right here, which form our base function here, what we're going to do is try to see what effect we have when we end up adding an a value to it. So let's just say, just to start off easy, let's start off with y is equal to 2x squared. So I'm going to purposely pick out a couple key points here. So let's actually compare the key points and see what happens. Well, first I noticed that the previous key point here in the base function of y is equal to x squared was -2 and 4. Now that got moved to -2 and 8. 1 and -1 and 1 over here now got moved to a negative, and I can actually write down here, -2, -1 and 1 now got moved to negative, oh, sorry, I'm just going to turn up the volume there, to -1 and 2. 0, 0 did not move at all. And this is actually called an invariant point. I know some of you had asked me about what that means. I won't put that on the test or anything, but just letting you know, invariant points are points that do not change with the transformation. Then we notice that the point 1 and 1 now gets moved to 1 and 2. And of course, this point right here, which is 2 and 4, now gets moved to 2 and 8. So what we notice is that the y value itself is being multiplied by 2. And that should kind of make sense, considering that the a value there is 2. So what we notice is that the a value really just stretches our stretches our graph vertically by a factor of 2. So that's why we had said that in the handout, that it's a vertical the a causes a vertical translation by a factor of a. And it's the absolute value of it, because if I switch this into a negative, you'll notice that we actually get the exact same effect. The only difference is that instead of it being, the only difference is that it gets reflected on the x-axis, right? So we still notice that we're multiplying by 2, but we're multiplying by -2 really, because we're reflecting it on the x-axis there. So we notice a bit more of a change. So obviously it's the rate at which it's increasing is basically doubling. You almost want to think of it that way, right? So we can see here that instead of going up by 1 step, we are now going down by 2 steps, right? The next one over here, it was 2 and 4. Now we can kind of compare it. It's going to move to 2 and -8. So notice that the y value is multiplied by the a value, which is -2 there. So that's why we notice that this is basically a vertical stretch. And because it's a vertical stretch, it affects the y coordinate, not the x. So it has no effect on the x, it's just changing the y there. And of course, one special, what if we had a fraction, right? What if we had something smaller? So what we notice is that if we have an a value that is between 0 and 1, or between -1 and 0, we actually will notice that our y values are decreased, right? So in this case, we are essentially multiplying the y values by half, which means that they decrease. So what was previously 1 and 1 now gets moved to 1.5. What the point that was previously 2 and 4 in the base function now gets moved to 2 and 2. And let's just practice a little bit more just so we see more of an effect. 3 and 9 would obviously get moved to, so here was 3 and 9, and now that's going to get moved to, and I can even spot the point here so you can see it exactly. It moves to 3 and 4.5. So it makes sense that the y values are simply being multiplied by a half. So obviously it gets smaller. So that's why we say it's vertically compressed by a factor of a half. And I know I personally always had a hard time with it, like, vertical, how do you tell if it's stretch, compression? What I would do if you're having a hard time with it, definitely look in the textbook. It actually, I think it's on page 69 in the textbook, section 1.8, has a really good summary of the different types of transformations. And as well, I posted a handout that Ms. Bao made that goes over the different types of transformations that we have, which is a really great resource you can use as well. So I hope that kind of makes it clear what happens with the A, what effect the A coefficient, the A parameter will have on the parabola, right? And what we kind of notice is that, if I switch this into, instead of having x squared, what would happen if I have a square root function? And I just want to show you that it really doesn't make too much of a difference. Obviously, some of the values may not be, you may not be able to find. Like I said, the domain doesn't exist for all values, so some of them are not going to exist in this case. But for the most part, when we look at the transformation, you're going to you notice something very similar. And let's just do a little comparison here. So we can once again tell that our base function, if we compare our base function, again, I'm going to pick a couple of points that are easier to read with square root functions. and you will actually notice that we have a very similar pattern going on here. So for example, the 0.11 in the base function for the square root function now gets moved to 1 and 2. The 0.4 and 2 in the base function now gets moved to 4 and 4, right? So I'm simply multiplying the y values by 2, right? That's really what I'm doing in this case, is I'm simply multiplying the y values by 2. So I'm just trying to write on here. So I'm multiplying them by 2 like that. And again, I can maybe show you in one more example here. So if we have the point, sorry, I'm just trying to get my marker going. The point here is 3 and 9. And what we notice is that if we multiply the y value by 2, we end up getting the point 3 and 6. So again, that hopefully kind of makes sense that it's the same. We essentially see that it's the same transformations that we're applying. We're just applying it to a different function. And that's the basic rule here, is that if you understand what's happening to one of these functions with the transformations, then you know how to do any type of function, really. We're just going to follow the same procedure for each of them. So going back to the handout here, just so we can kind of compare what we're doing next. So we talked about the a value, and again, I haven't done it with absolute value function, but I guarantee you it's going to work the exact same way. And let's actually do the absolute value function. So let's just practice a little bit more. Let's just see a little bit of a comparison here. And we don't have to use that number there. Perfect. So let's just compare it and see what happens with these different functions here. So this is going to be 2x. Let's just say I make it, oh, sorry, that's wrong. 2 outside of the absolute value function, and then x. So notice once again that when we compare the purple graph, which is the function of y is equal to 2 absolute value of x, we just noticed that our y value is simply being multiplied by 2 each time. So we notice that it's the exact same transformation that we expected for quadratic functions and absolute and square root functions. It's going to be the exact same thing for for an absolute value function, and it would work the exact same way for reciprocal functions as well. So I'm hoping everyone kind of understands that. And it's the exact same idea, by the way, if the a value is less than 1 or it's between 0 and -1. We again notice that if I switch this to like a half, it simply is this divided by 2, right? Or multiplied by half, so it's getting smaller. So that hopefully answers the first question here. So obviously, if it's negative, we talked about this, it's reflected on the x-axis. And of course, it is stretched vertically by a factor of a. And we always use the absolute value of a to indicate that if it's negative, then it's still going to be stretched or compressed by whatever the factor of a is. Okay. What about Q and P? So what I want to be clear with on the textbook, sometimes they'll use different notations. So P, they're talking about in the textbook, they'll normally use a D variable for that. And basically, in this case, we're moving left or right. So in this case, we are going to the right. And again, it's going to look negative, but it's actually going to the right. And this is going to the left. And for Q, this one's pretty easy. This is also going to be known as the C variable in the textbook, at least. And in this case, if it's positive, you'll go up. If it's negative, you go down. So pretty self-explanatory. And again, I'll show you this one in decimals, although I think this, the vertical and horizontal translation, I think most of you had an easy time with that. I don't think that that was the big issue. So I can even show you on this graph here. So let's say I have, and I might as well use an absolute value function here. So I write down y is equal to, so this is my parent function. And let's say that I am going to have a translation to the right, and then I am going to add 5. So what do we notice here? Well, I noticed that my p value is 3, and I'm going 3 units to the right. So what I'm really doing is I'm taking my parent function here, I'm moving it 3 units to the right, and then I'm going to be going 5 units up like this. So 1, 2, 3, 4, 5. Now, when it's just vertical, and when it's just vertical and horizontal translations, actually makes it really easy. All you really are doing is you're just kind of moving the whole graph all together. You're kind of shifting it together when you're just shifting it left or right, up or down. It's when it gets really tricky is when you have horizontal stretching compression or vertical stretching and compression. Then it gets a little bit tricky to kind of do all of them at the same time. Okay, so I hope that kind of explains it. And again, even if you had a different kind of function, so I'll show you a different example here. Let's do reciprocal functions. I feel like we sometimes ignore these ones. And it's just good for you to kind of see, what would happen if I switch, if I do that change to a reciprocal function. So let's check this out. So again, we kind of notice that in our reciprocal function right here, we simply take, it's almost like what I would almost suggest is taking points or almost recognizing what the center of the actual parent function is. And one thing we notice that's very special, the one point of the reciprocal function that stands out is where the vertical and horizontal asymptotes meet. So it seems to be at the origin here. And what we notice is that if we take that origin and we simply move it 3 units to the right and 5 units up like this, we end up at where the new origin is going to be, which is now going to be 3 and 5. And notice that the vertical asymptote, it used to be at x is equal to 0. Now the vertical asymptote is at x is equal to 3, which kind of makes sense because if you do a little bit of math here, you probably will notice that if you sub in 3 there, you get 1 divided by 3 minus 3, and obviously 1 divided by 0 is not defined. So it kind of makes sense that the vertical asymptote would be 3 there. And again, it should make sense that we're taking our vertical asymptote and moving it 3 units to the right. And of course, our horizontal asymptote, which I will do in a different color so you can recognize it. Here's my horizontal asymptote. I noticed that this horizontal asymptote gets moved up to y is equal to 5. So it got moved 5 units up. So it kind of makes sense that we would move, since we're moving the whole entire graph, we're also moving our vertical and horizontal asymptotes as well. So I hope that kind of makes sense with the vertical horizontal translation. And then, of course, knowing that, we can definitely do the examples on the handout. And hopefully it'll be a little bit easier now that I have a better pen here. So, of course, we have our parent function. Again, there's different ways to do this, but I'm going to start off with the parent function here. I know some of you are more familiar with just finding the transformation by graphing it all in one big step and then just applying the transformation step by step, or you can use the mapping rule that we discussed in the handout, right? So I posted a review handout that Ms. Bao made, and she kind of goes over a summary of the mapping rule that we can use. It's kind of a bit of a shortcut we can use to find the transformations. So in our case, what we're going to do is simply apply each of the transformations step by step. But again, remember, you always want to stretch vertically or compress vertically first before you translate left or right, up or down, before anything else. So in our case here, we are simply going to reflect this first on the x-axis. And of course, we are multiplying the y values by half. So it's basically looking like a smaller V shape like this. So the 0.00 didn't change. The point negative, this was -1 and 1, now gets moved to 1, -1, and negative a half. The point -2 and 1, and -2 and 2 now gets moved to -2 and -1. And I'll do maybe one more. The point -3 and 3 now gets moved to -3 and negative a half. So we kind of have a V shape like this, but it's just a little bit flatter. You want to think of it that way. So it kind of roughly looks like this. So not looking like a great graph. And again, it's not very detailed, but it's definitely better than the one that I did on Smartboard. And now we are going to take this graph and move it 2 units to the right. And again, it looks negative, but it's actually positive. We're going to move it 2 units to the right, and I'm going to do this in a different color so we can actually see a difference. So move each of these points 2 units to the right. So we have it right there. This one gets moved over here. This point gets moved over here. We're just moving everything to the right. And this one right here gets moved over here. And then this point right here gets moved over here to 0 and 1. So we can roughly see that it kind of looks like this. So still a V shape. It simply just got moved 2 units to the right. And then of course, our last step here, we move it 3 units up. So we are gonna go 3 units up here. So we go 1, 2, 3. And that means that we end up at this point right here, which is at 2 and 3. So it almost seems like our origin got moved to 2 and 3. You want to think of it that way, right? So now we simply draw out the rest of the points. So this one got moved 3 units up. This gets moved 3 units up, so it's right there. This gets moved 3 units up, so it is now at 4 and 2, and we follow the same procedure here. So it kind of looks like that. So there's the graph that we have in the end. So I hope that kind of makes it more clear. With reciprocal functions, I'm going to avoid that. Again, nothing wrong with it. It's just that we're normally not going to consider, when the a value is not equal to 1 in with reciprocal functions. But again, you can do a bit of a quick sketch just based on what we discussed. We will notice that because we're moving to the right, the vertical asymptote, instead of being at 0, this is where it would have been. Now it's going to get moved to 1. And the horizontal asymptote is instead of being at y is equal to 0 right here, it's going to get moved to -3. So just kind of roughly speaking, we kind of notice that the vertical asymptote is now going to be at x is equal to 1 and y is equal, and the horizontal asymptote is going to be at y is equal to -3. So again, this is going to be important for you to just understand so you can match the graph, but it won't actually make you graph it from scratch there, not for reciprocal functions. And let's do another one with the square root functions. So again, we graph out the original function, and I'll do this in green here. So the base function in this case, the first thing you have to recognize is what is the base function. So essentially you look at this function, you say, okay, well, whose parent does it, like which of the parent functions does it look like, right? Which one does it resemble the most? And I hope everyone can recognize that this basically is a square root function, right? The square root function is the base function here. So that means that we're going to be transforming the points 0, 0, 1, 1, 4 and 2. And I know some of you had asked, like, do you have to memorize this? I definitely think you should have it memorized. It's going to make it a lot easier, right? So you should definitely know at least some of the key points on each of the parent functions. So not the reciprocal one, but definitely the square root function, quadratic function, and the absolute function. Okay. So what we're doing in this case is we're simply applying the transformation step by step. So let's start with the a coefficient here. So it's going to be -2. So that means that this is going to be reflected on the x-axis. And of course, because it's the absolute value is 2. So because the absolute value is 2, we know that it's going to be a vertical stretch. Right? So we're going to be vertically stretching in this case. So that means that we're going to go to, we go from 0, 0, that doesn't move. Then we go to 1 and 2, sorry, 1 and -2. The next point we go to, we were at 2 and 4, but now the 2 and 4 is going to get moved to, sorry, we were at 4 and 2, that's what I meant to say, 4 and 2, and now this is going to get moved to 4 and -4 right there. And again, all we're doing is simply stretching it out and reflecting it on the x-axis. So it kind of makes sense that it looks like that. And then our last 2 steps here, and we can honestly do this all in one big step. And now that we're hopefully a little more proficient with this, we're going to move it 1 unit to the right. And again, it looks negative, it's actually positive, and 3 units up. So take each of these points and move them 1 unit to the right, and then move it 3 units up. So 1 unit to the right, 3 up. There it is. And then 1 unit to the right, sorry, 1 unit to the right, and then 3 up. There it is. And then 1 unit to the right, and then 3 up. There it is. And I think I got everything there. And I think I made a mistake here. Sorry. Yeah, I totally made a mistake. Sorry. Let me just fix that up. So this one's going to be 1 unit to the right, and then 3 units up. So it should go... I feel like I made a mistake here. Yeah, because it's going to be... Oh, no, we're good. We're good. Just double checking here. Yeah, no, we're good. So it's going to move right there. Perfect. And then we close our graph, and then we simply have our new transformation there. So a different way to do this, and we'll talk about this, is to map each of them step by step. But I will kind of hopefully make sense of it once we talk about the last parameter here, which is the k value. And I think this is where some of you are definitely struggling with. So I'm going to go to the next part, if that's okay. So I'm going to erase this. And I hope you're right if I just move on to the next part here. So now we're looking at the transformations of common functions. So still the base functions, but now we're looking at when the k value is what happens when we have a extra k value. So one thing you really need to be careful of, do not confuse this with the a value itself. I know that they look similar, and I think this is where there's a lot of confusion. People tend to confuse this with the a value. Remember, the a value is affecting the output, again, because it's vertically stretching it, so it affects the y, the output, not the x. This is affecting the x because it's inside. We're applying that transformation inside the input, right? So very similar to what we noticed with the p variable. Since it's actually going into the input, it's going to be affecting it. It's going to be affecting the x coordinate, right? So once again, we notice that this is going to affect the x coordinate, not the y coordinate. So one thing you should have done when you fill this in, and I hope everyone actually did fill this in, you'll notice that the x values were picked out very purposely, right? If we, in our case, with our regular parent function, we end up getting 9, 4, 1 in order 0, 1, 4, and 9. And what you'll notice is that if I take each of these x values that I purposely picked out, you will end up getting the exact same y values, 9, 4, 1, 0, 1, 4, and 9. You can even check yourself that that's correct. And of course, this one, we end up getting the exact same values, 9, 4, 1, 0, 1, 4, 9. So what we notice is that our y values are staying the same. It's our x values that are changing. And it's not changing by what you would necessarily expect. So I'll kind of draw this out for you, and you can actually compare it. So we have 0, 0, 1, 1, 2 and 4, and 3 and 9. And again, you can always tell me if I made a mistake here. Yes, I think we're good. Okay. Okay, so now I'm going to do it in a different color here. I'm going to take my next graph, so it's going to be 3.5. And I am going to be mapping out 3.5 and 9. So 3.5 is right in between, and it goes to 3.5 and 9. Oops, I just realized maybe I need to switch the color. Oops, there we go. So we have 3.5 and 9, and then the next point we have -1 and -1 and 4 right there. And then we have -0.5 and 1, so that's right there. 0, 0, and then we have 0.5 and 1, which is right there, and then we have -1 and 4, and then of course 1.5 and 9. So the parabola is roughly looking like this. And again, this one's going to be a little harder to draw. It's more squeezed in. So what we notice is that we get the exact same, we reach the exact same y values, but we reach them in half the time. And that's why I think I mentioned this to some of you in study hall and in the class as well. I personally think it helps to think of the k value as speeding up or slowing down your function. So if I have a k value of 2, what that really is doing is it's making my function move twice as fast. So if it's moving twice as fast, I'm reaching the same y values, but I'm reaching them in half the time. So what I notice is that if I take the previous points in my parent function, all I really need to do in this case is simply take those points in the parent function and then divide the x values by 2, right? And for the points that have the same y value. That's all I'm really doing there. And and again, the reason we're doing that, and the reason we see that is because the function is, so when I have a k value of 2, for example, it's making my function move twice as fast as it would. So when I sub in the x values, I'm basically multiplying that by 2, which means I reach the y value of the x value that will come up in twice the length as before, right? So that means we reach the same y values, but we reach them in half the time. And because of that, we notice that it ends up looking like it's horizontally compressed. So notice that you would think that it's horizontally stretched. It's horizontally compressed because what we're saying is that the x coordinates are being divided by that value, right? So instead of getting the x values getting bigger, it's actually getting smaller. And then we kind of notice the opposite for this one here, and then we'll graph this out right next to it so you can actually see a bit of a difference. And I apologize, I know it's going to get a little messy here. I don't know how much I can erase here. That's okay. Let me just switch the color here. Sorry, let me just try to switch this here. Oops, that's actually not what I wanted to do. But I don't know how to go back here. Okay, that's okay. I'll just start from the beginning. So let's compare the parent function here. I'm just going to quickly do the parent function. Okay, there's our parent function, roughly speaking. And again, I'll show you on decimals later on because it's going to look a lot better. This one is not looking as good, but that's okay. And then what we're going to do is we're going to plot out these points. So we have -6 and 9. So -6 and 9 means we go over here. Oops, and I have to switch the color. -6 and 9 is right there. And then we have -4 and 4. So -4 and 4 is right there. Oops. Yeah, we're good there. And then we have -2 and 1 right there, 0, 0. And then we have 2 and 1, and then 4 and 4, and 6 and 9, which is right there. Sorry, it's just getting a little harder to draw here. Perfect. So what we noticed once again is that just kind of what we saw before, this is affecting just the x value, but it's a different type of effect. And again, it's kind of the opposite of what you think. So you think the k value is a fraction, it's smaller. It would be basically, you would think it's a compression, but actually what it's really doing is it's horizontally stretching it by a factor of the reciprocal, which is 2. So again, you would think that it would make the x coordinates be multiplied by half, but it's actually it's making the x coordinates be multiplied by 2. And the reason for that, and this is the best way I think of it, that k value of a half basically means that it's going twice as slow. So you're reaching the same y values, but you're reaching them in twice the amount. So because of that, the x values themselves are multiplied by 2. Does that kind of make sense so far? Hopefully that's good. So what we're really doing is simply multiplying the x coordinates by 2. So there's a general rule here because we're kind of doing the opposite or the reciprocal, what we would think. We can simply say that we're taking our x coordinate and simply dividing by k, or that we're multiplying by the reciprocal of k. That basically means the exact same thing. And we can follow the same concept with the square root function, and you'll notice that you will actually follow the exact same procedure here. So we have in this case 1, 0, 1, 2, and 3, and then of course this is going to be 0, 1, 2, and 3, 0, 1, 2, and 3. And what this graph is basically going to look like is kind of what we saw before, a transformation, right? So we have our parent function. Let me switch back here. Zero, 0, 1, 1, 2, and 4. So it kind of looks roughly like this. And so in that first one here, we have, we notice that everything's going to be more stretched, it's going to be horizontally compressed. So it's not going to get moved to, there we go, a half and 1. So 0, 0 doesn't change. A half and 1, 2 and 2 is right there. And then of course, let me do one more here. 9.5, and 3. So it's kind of looking like that, right? So it's horizontally stretched, compressed by a factor of a half. And again, it looks like it's vertically being stretched. And this is where it sometimes gets confusing. But remember, what we're doing here is horizontally compressing it by a factor of a half. And let's do the last one over here. And again, I'll do this in green here so you can kind of see. And I'll do in red the last one here. Oops, it's not showing the color. There we go. So we have y is equal to the square root of negative x. So once again, what we notice is that this is going to take our previous function in blue and is simply going to reflect it on the x-axis. So instead of going 0, 0 to 1, 1, we go 0, 0 to negative 1 and 1. And then we go to negative 4 and 2. And then, of course, the last one we have, I think there should be space here, negative 3 and 9. Sorry, negative 9 and 3. That's what I meant to say. And so then we can see here that this is our reflection on the y-axis there. So again, kind of similar to what we saw with our transformations with the a value, we notice that the k value, if it's negative, it's just going to be a reflection on the y-axis instead of an x-axis. So I'll just kind of show you on Desmos kind of what this looks like. And I hope this kind of helps you out. So you can kind of see, you can kind of compare the horizontal and vertical compressions here. So let's say that we have, I'll actually do it for absolute value function. You're going to see this exact same idea for all of them, right? So I'm just going to purposely show a couple key points there. Okay, so hopefully that helps. And we have negative, I'm going to add a couple more, negative 3 and negative 4, perfect. So let's see what happens when we have a k value here, what it does. So the absolute value of 2x, what we notice here is that it takes our previous y value here, and it doesn't change it at all, right? The y value staying the same. What we notice is that the x value now gets moved to negative, 1.5 and 1. This y value, this point that used to be 2 and 2, now gets moved to 1 and 2. So we notice once again that it's the x coordinate that's being changed now, not the y coordinate. And what we're really doing is we're simply dividing the x coordinates by 2. So the x coordinate is being divided by 2. Think of it that way. Okay. And again, it should make sense because the k value is telling you how fast you're moving. So in our case, since we have a k value of 2, that means we're moving twice as fast. So that means we reach the same y values, but in half the time. So we are taking our x coordinate and simply dividing by 2. So this point that was 5 and 5 now gets moved to 2.5. Sorry, 2.5 and 5. And it's the same concept here on the left-hand side. So negative 1 and 1 now gets moved to negative, now gets moved to negative 0.5 and 1. Negative 2 and 2 now gets moved to negative 1 and 2. So again, we're noticing that we're just dividing by 2 each time. So same concept here. And then of course, let's do one more. Negative 3 and 3. We notice that gets moved to 1.5 and 3. Sorry, negative 1.5 and 3. So we're simply taking our x coordinate and dividing by 2 each time. So we notice that that's another way of saying multiplying by the reciprocal, really. So hopefully that kind of is starting to make a bit more sense. And this would work for quadratic functions, square root functions, reciprocal functions, or absolute value functions, right? And then of course, if you have a k value of 0.5, just like what we saw with quadratic functions, we basically notice the opposite effect. Essentially, we just take our previous x values and we simply multiply them by 2, right? And again, I'm just going to purposely, oops, that's not what I wanted to do there. I'm going to purposely show a couple more here so you can see it, 3 and 4, 5 and 6. So we can kind of notice that in our case, we have, for example, the point 1, 1 now gets moved to 2 and 1, right? So we notice that the y-coordinate stays the same. It's just the x-coordinate that switches. We multiply by 2. The point 2 and 2 now gets moved to 4 and 2. The point 3 and 3 now gets moved to 6 and 3. So it's the x-coordinates that's being multiplied by 2. And this point right here, that was 4 and 4, even though you can't actually see it labeled here, but I'm going to draw it myself. You can see that that gets moved to 8 and 4. So it makes sense. Again, we notice that our x-coordinates are being multiplied by 2. So our x is being multiplied by 2 in each of these cases. And again, it should make sense because a k-value of a half basically means you're going at half the speed that you used to go. So you're going basically twice as slow, right? You're going half the speed. So that means that you're going to reach the same y values, but in twice the time. It's going to take you twice as long to get there. Right, so it would make sense that the x-coordinate would be multiplied by 2. So I know it just kind of plays with your mind sometimes, right? You think it's, you would think in this case it would be getting, the x values would be getting smaller, but they're getting bigger. So in this case, we take our x value of 3 and we multiply by 2. We take our x value of 2 and we multiply it by 2, which gives us 4 and 2. And again, the y value stays exactly the same. And so that's really the whole concept here. Hopefully that kind of is making sense. And of course, we saw with the transformation, that when there's a negative sign in front, all we really do is simply reflect it on the x-axis. Although with absolute value functions, you're going to notice it makes no effect at all. Same with quadratic functions. Hopefully, I don't know if there's any more questions about that, but I hope that kind of clarifies a couple of the questions here. I know some of you were just a little bit confused about how to do that. Now, I didn't actually correct these questions on here, but what I would suggest is that you actually try graphing them out on the space if you want. I'll be honest, this one right here is going to run out of space, so is this one. I know some students tried this in class and we're a little frustrated because it's not even fitting in the graph here. So I would definitely recommend using graph paper if you're doing this, or use Desmos to kind of go through the steps. So I can actually show you how to do this one on Desmos. So we have the square root of 3. So I want to just kind of go through this step by step. So let's just say you want to know what this graph looks like, and we'll kind of use technology to kind of guide us. So we start off with our parent function, which in this case, we look at our graph and we say, okay, well, which function seems to be its parent, right? Which one does it look most like of all the parent functions? Well, we can hopefully notice that this essentially stems from the base function of the square root function, right? This is a base function here. So that's our starting point there. So I would just plot out a couple of the key points. And again, if you have the graphing technology, you can just graph it, or I would still plot out a couple of the key points here. So I have 4 and 9 as well. So what I'm going to do now is I'm going to apply these transformations step by step. So my next step here, I notice that I'm going to have a k value of -2. Now there's one little change here, and this is something that I know I forgot to mention this yesterday in the lesson. In this case, you always want to get it in the form, the transformation form that is given to you in the first place, which means that the k value needs to be factored out. So I factor out the -2 here, and this ends up giving me x minus 1 x minus 1 in bracket, in the square root minus 3. So you want to make sure that you factor out that k value first if it's not already done for you. So now let's think about all the transformations here. Let's start with the A transformation first, right? So we know that this is going to be a vertical stretch by a factor of 3. So that means that all these points right here, what we're going to do is we're going to take the y coordinates and we're simply going to be multiplying them by 3. So let's see what happens in all the key points. And again, I wouldn't pick this one here. This is not a very easy point to read. I would just pick these points right here, the 4 points I've listed off there. So 0, 0, luckily, it's a very easy one to work with. Nothing happens there. 1 and 1 gets moved to 1 and 2. 4 and 2 now gets moved, being multiplied by 3, I forgot. This is going to be moved to, so 1 and 1 gets moved to 1 and 3. And of course, 4 and 2, I'm going to have to make some space here, is now going to get moved to, and I'm going to have to, even with Desmos, we're going to run a little bit out of space. So this will get moved to 1 and 3, and this is going to get moved to 4 and 12. Oh, sorry, not 4 and 12. Sorry, my bad. Because we're multiplying by 3. Is that correct? I just need to go back a little bit. Sorry. Yes, so we are multiplying it by 3 in this case. So this y coordinate right here of 2 is now going to get moved to 6 right here. So it's going to be 4 and 6 like that. So this is roughly kind of looking like this. And again, there's one that I think we're going to run out of space here. 3 times 3. Actually, we might just make it. So we have 9 and 3 right there. So it's kind of looking like this, more or less. So we're stretching it vertically by a factor of 3. What do we do next here? Let's read the next part. Then we are asked to stretch it. Sorry, we have a k value of -2, which means that we're going to be horizontally compressing it by a factor of by a factor of a half. And again, when you talk about the factor that it's being stretched or compressed by vertically or horizontally, we always ignore the negative sign, right? So for two things, we reflect it on the x-axis, and then we apply the horizontal compression in this case. So we go back to our graph here, and we are going to essentially just take our previous values here, and we're going to reflect it on the x-axis. So now we have 0, 0, nothing happens there. So I'm actually going to change this because I want to be able to see it. There we go. So this is going to be reflected on the x-axis right here. And again, remember, it's going to be each of the x values is now going to get multiplied by half. So this point right here that was 1 and 1 now gets moved to -1/2 and 1. The other point here that used to be at 1 and 3 now gets moved to -1. Sorry, 1 and 3 now gets moved to negative. Sorry, we are just multiplying by a half here. Sorry, I'm just checking here. Oh, sorry, I did this wrong. Sorry, I was looking at this one, but we're not changing that. That's changing the parent function, but we're going for the last step here. Sorry, I made a mistake here. That's going to be at 1/2 and 3. And the next one over here, we are changing this point right here. So this is at 4 and 6 right now. So we simply take our x coordinate and we take half of that, which is going to be 2. And our y coordinate is going to be the same. So it's going to be 2 and 6. And let's do the last one here. This is going to be 9 and sorry, it's hard to read here because this is in the way. 9 and 9. So 9 and 9 is now going to get moved to it's going to get moved to 4. Sorry. Just move that out of the way. 4.5 and 9 right there. So it's kind of roughly speaking, kind of looking a little bit like this. Right? So there is what we have for our our A and K values. And then of course, the last couple steps here are actually the easy parts, I hope. You simply are going to move it 1 unit to the right and then 3 units down. And we can kind of go step by step with the points that we have already. So 1 unit to the right, and then, sorry, I'm just trying to get this to work here. For some reason, this marker is not working now. Okay, there we go. I think it works now. So we're going to move it 1 unit to the right and then 3 units down. So 1 unit to the right, 3 units down. That means we move over here to 4.5, sorry, -3.5. So -3.5 and 6. This is going to go 1 unit to the right and then 3 units down. So that gets moved to -1 and 3. And 0, 0 does not move at all. So I think that just gives us enough points so we can kind of work with that. And oh, well, yeah, of course, 0, 0 does move. Sorry, I just need to move the other ones here. So we have a half, and then we of course move down to 0 on the y coordinate. So we're just moving each of these points in orange 1 unit to the right and 3 units down. So that gets moved to a half and 0. And of course, the last one, 0 itself, is going to get moved to, hopefully I can move this. Sorry, guys. Let me just see if I can move this around. Okay, it doesn't seem like I can move. So let me just move this mouse around there. So the 0, 0 is now going to get brought down to 1 and -3 right there. So it's going to look, roughly speaking, something like this, right? So it kind of still resembles like a square root function, but it just looks a little bit different, of course. And of course, you can always check that the answer is correct by doing the graph, right? So let's type it in and see what we get. So we have y is equal to, and I'm just going to check again that I have all the right information. Y is equal to 3. For some reason, I can't click on this. Y is equal to 3, and then square root of x 2. So it's -2x minus 1 plus, and then what do we have here? -3. Yeah, and we actually noticed that it's pretty much the exact same graph we got. It just obviously looks a little bit different, but it's pretty much the exact same graph that we got, and the points seem to be at the same spots there. So we did this correctly. So hopefully that kind of makes sense. And again, I just wanted to just make a video here. I know it's even the video itself is long, just to kind of re-explain some of those concepts, because I know that they were a little bit tricky. I still recommend that you read over the note that was given by Ms. Bao about the mapping rule that we can use. So I'm hoping that kind of makes it more clear. There's a bit of a shortcut that you can use. Basically, the whole idea there is that if I give you an x coordinate, and actually I can maybe write down the rule here at the bottom if I have a bit more space. Yeah, I'll try to squeeze it in here. So the rule here is that if I have an x and y coordinate, I can simply take my x and y coordinates, and I know, and I'm going to apply the transformation step by step. I know that the a, and again, let's just go back to basics here. I know that if I have any function like this, and I have a outside of the brackets there, that's going to be affecting the y. This affects the y. The k right there affects the x. Then I have x minus d, and of course, because this is inside the brackets, this is going to be affecting the x as well. And then I'm going to be adding some other parameter, which will be affecting the y, because it's outside of the input. So the 2 in the middle affect the x. So it's a good way to remember this. This affects the x. And sorry, I'm trying to get a different color, but it doesn't seem to work there. Okay, let's try this. Oh, there we go. This affects the x, and then these 2 at the ends affect the y. So because we know that each of the parameters only affects either the x or the y, it actually makes it easier to come up with a rule for this. It's not like one of these parameters is going to be affecting the x and the y. It just does one at a time. So what we really notice is that we can take, if we want to figure out what the new points are going to be in the transformation, we can simply take our x and y coordinates, and we're going to be applying these operations. So for our x coordinate, we know we're taking our x coordinate and dividing by the k value. And the reason we're dividing by k is because we're multiplying by the reciprocal of k, which we already saw, and multiplying by the reciprocal is the same as dividing by k. And then, of course, we move it left or right, depending on what the d value is. So we simply add if it's positive, and we subtract if it's negative. But another way of saying that is simply to add the d value, because of course, if it's negative, then we're going to be subtracting anyways, right? And then for the y, we are going to be taking the a value and simply multiplying by whatever the y coordinate is. So we write that down as a times y, and then we simply add on whatever the c value is. Now, keep in mind that with this rule, we also could have done x over k plus p. Again, you can use p instead of d, it doesn't make a difference. And then, of course, here we have a y plus q, like that. So I hope that kind of makes more sense, and I hope that this kind of adds on to the lesson from yesterday, especially for cohort B. I apologize that you had no good technology, and it was probably one of the hardest lessons to kind of just read on your own. But I hope that this makes a bit more sense. Let me know if you have any questions. But of course, I think for the test itself, you should be fine. Remember, I'm going to be mindful of the fact that you're learning this in a very fast way, so I can't possibly test you on everything. But just make sure you know how to apply these transformations and how to recognize the transformations as well. So I hope that all makes sense. And again, good luck. Best of luck with the test today, and I hope it all goes well.